Good morning and afternoon and evening to everyone, wherever you are. We are now approaching over 100 attendants. So I'm just going to take the floor for a very short moment, only to introduce the speakers, and then I will let them go. We have 3 speakers today, as you can see from the cameras on, and they will speak in this order. So we have Hugo de las Heras Gala. He's an officer for quality assurance at the BFS in Germany. From the same institute, we have Maximilian Göppel, again, a physicist also. And then we have Matthias Anton, who's working in the PTP, in the X-ray diagnostics at the National Metrology Institute of Germany. So they have, this is not the first time we have multiple speakers in the CCRI webinar series. And these are their titles. Everything revolves around the interface between dosimetry and diagnostic radiology and imaging. So this is quite an unconventional webinar in the series of the CCRI, but we are very much happy to have them speaking in a moment. And so they will speak in this order. Hugo de las Heras Gala on the introduction to the problem of dose efficiency in computed tomography. Maximilian Göppel will talk about type testing of CTs using the model observer approach, a suggestion from an automated analysis. And then closing will be Matthias Anton on image quality parameters derived from patient images and approach using non-parametric statistics. So with that, I'm going to leave the floor to Hugo de las Heras Gala. I'm going to disappear for the moment, and then at the end of the 3 of you, I'll be coming back to read the questions and address the audience. So Hugo, I will stop share now, and you can go ahead.
Thank you so much for inviting me to give the introduction. This is particular thanks to Matthias and Max, because they allow me to present their work. And I'm going to tell you all something about what is the problem we have in this field right now. This is a CT device. Most of you have seen it, and if not, you may see it in the course of your life, because in fact, most of us will be patients at some point in life. So one of the issues I wanted to be familiar with is that the CTs have a certain way of dealing with data, and this is called reconstruction. Some of you will be familiar with that and some others don't. So what happens inside the CT is that an X-ray tube irradiates the patient, and there is a row or several rows of detectors that get that radiation. They are analyzed in a computer through this thing called CT reconstruction that produces in a monitor the actual image that we're used to see from the medical doctors. So the largest contribution to man-made radiation burden comes indeed from CT examinations. And this is the data we have in Germany from 2021. 11% of the diagnostic procedures are CTs, but from the collective effective dose, the CTs made up for 71%, which means something like 1.5 millisievert per year delivered to a population in Germany from CT. And this also is related to something between 1 and 50 millisievert effective dose per each examination of CT, so that you know what kind of doses we're speaking about. The numbers in France, since this seminar is organized in France, are very similar, and they are also increasing in this trend. So let me show you what CTs can do. You can actually see heart beating in vivo. You can see arterial occlusions that you would not be able to see if you don't open the patient. And you can also see this kind of slices that we're more used to see. But you can also do this kind of stuff. And indeed, when you see it, you don't really know what it is, but it is a tomography of a nose, and it actually won a contest of images in science from the journal Science. And this is definitely not what we want to do in diagnostic radiology. We don't need pieces of art. We need something that is appropriate for the use that it has to have for the clinical indication. Because if we lose control of the quality of the images and we don't have certain assurance methods, we can have certain problems like we had during the time I was working in the FDA in 2009. There were something like 206 cases of overdose from one CT in a clinic in California, and people were getting a scan of their head, perfusion scan it's called, and they were losing the hair in that stripe after a few days, something like 1 week. So they were not, the medical doctors were not linking that to the CT until 206 cases had already happened. And therefore, I hope you are a bit motivated to learn a bit about the image quality of CTs. And let's start with this structure of noise, which is something you will have to master to also get the best out of the next presentations. And look at this. If you're looking at the images that you see in the computer, you will probably see the details of Albert Einstein. But if you go away, far away from your computer, and let me help you do that, you will see better the image of Marilyn Monroe, I guess. So this is because both images are superimposed, and the image, the perception of our images is really very influenced by the frequencies. And in this image, we have the large frequencies representing Einstein, and the low frequencies are representing Marilyn Monroe. So that's why, depending on how you're watching at the image, you will see one part or the other. And this is also affecting the detectability of signals, such as tumors, in diagnostic radiology. This is also strongly dependent on frequency. And look at this example. If you have a very homogeneous background of noise, and you superimpose a signal, you have an example like the thing we see here on the top right. And if we do that with different contrast to noise ratios, which means higher contrast here, lower contrast in the bottom, you can see that the detectability is very much different. But what happens if we change the structure of the noise? Even preserving the contrast to noise ratio, like in the middle row, with a different structure of noise, we cannot say that here on the right you can detect any kind of signal. Whereas for the same contrast to noise ratio, if the frequency of the noise is different, we can detect a signal here. So let's see this in a clinical example from CT. Because in fact, current CT reconstruction algorithms also affect the structure of the noise, so the frequency spectrum, and they are indeed affecting the detectability of lesions. Look at what's happening with the most traditional reconstruction algorithm, which is called filtered back projection. This is a phantom they used in a clinic in Berlin. With a signal here, you can definitely detect this signal. And if you take the same image of the same phantom with another iterative reconstruction, which is in the market since 2012, but you do it with a very much lower dose, look at the dose values are something like 6 times lower here, but you actually changed the detectability of that signal because the frequency spectrum is much different. It's very different. So this is something to take very much into account. And how does quality assurance in CTs work? So to avoid this kind of stuff, let me show you. In general, people are using this kind of subjective analysis of images, looking at them, but we can also have more objective ways of doing quality assurance. We can have anthropomorphic phantoms so that we can irradiate these pieces of whatever material as much as we want and test the device, but we can also use certain technical phantoms that can be analyzed for resolution, for contrast, for noise. And this is what we're doing now. But before iterative reconstruction arrived around 2010, assumptions of linearity and shift invariance were granted, which means something that is not happening right now. And I want you to see one example. Let me show you what modern algorithms are actually doing. They are local and nonlinear because look at the left, you see an example of a very typical algorithm for a clinical reconstruction of a patient, and you have on the bottom, the middle, the same reconstruction of the same patient with another algorithm. And let me show you the most modern kind of reconstruction, which is a deep learning based algorithm in the market since 2022. If you look at this region of the phantom, you will see that the most modern one has a very blurred, actually a very homogeneous noise, a very low noise. But at the same time, if you look at that other portion of the images, you will see that the algorithm is preserving the edge very well, which is the opposite of blurring. That means the algorithm, especially here on the right, is doing something completely different in a certain portion than in another portion of the image. So how can we know that the algorithm is also dealing well with details that are within the patient? That is one of the problems, that the assumptions for traditional quality assurance do not hold. We cannot be sure that the algorithms with clinical patients are doing exactly the same as with our technical phantoms. So how can we update quality assurance? That's why Maximilian Goepel and also Matthias Anton are giving you their talks today. And I'm also looking forward to hearing them.
I'm also very happy to be able to present the work in this webinar, and I will jump right to the topic. So welcome to all to the second talk in this webinar, which will highlight a method developed to assess the dose efficiency in computed tomography. The talk will cover certain topics. So the first one will be about model observers. So what are observer studies and especially the channel mechanism? The next part will be about the dose efficiency. So an overview, short look into the automatic image processing, and description of the phantom, the protocol, and the figure of merit. Subsequently, I'll show some results. And last but not least, I will give a summary and an outlook. But before we start with model observers, I will add something to the previous talk. So Hugo already introduced the image reconstruction that is needed in CT, and also the filtered back projection and the iterative reconstructions were shown. So this is kind of a repetition, and this will be helpful when we come to the results. So the filtered back projection is just using the projections organized in a sinogram and is back projecting into the image space. It's quite stable and has a low computational demand. The hybrid iterative reconstruction technique is quite similar. However, it has a filter on the sinogram to reduce artifacts, and there's an additional filtering on the image to reduce the noise. And the third option here is the model-based iterative reconstruction. And this is different from the other two in the way that after the back projection step, it uses a forward projection, so from image space back to the raw data space. And in this forward projection, it is able to include system geometry and noise models. And in this way, it iteratively works until it's happy with the image and it stops. So to add some images to compare those, we have already seen some in the first talk, but here we have another comparison. So we have a human heart that was scanned. At the top row, we have 4 milligray, and the 3 bottom rows are using only a quarter of the dose. And we have the filtered back projection and also the other 2 iterative reconstruction algorithms here. If we compare them in terms of speed, we have a range from fast to quite slow with the model-based iterative reconstruction. However, on the other side, we have a pronounced noise reduction with the model-based iterative reconstruction, which can also be seen on the right. If you compare the bottom row with the top row, the noise level is quite similar at only a quarter of the dose. And together with the noise reduction, we can also look at the dose reduction potential. So this is also an advantage that those iterative reconstructions offer. But now, after this short slide to the image reconstruction, we can come to the model observers. So we can use low contrast objects. So those objects that are hard to detect on images, and assess the detection of those using model observers. So starting by images of a phantom, we can define regions of interest, both with and without the object. And we need usually more than 100 of those regions of interest. Those are then scored either by a human observer or, as in our case, a model observer, which is a mathematical algorithm. And this model observer uses a template, and by applying the template to the regions of interest, it derives an observer response. So from each of the two groups, we can derive a distribution of observer responses as shown on the right. So from those two, we can then take the mean and the standard deviation and calculate the detectability, so a figure of merit of how good the observer is able to discriminate between the two groups. It is the signal-to-noise ratio of the test statistic. And to give you a feeling for the detectability, if you have a value of 1, it corresponds to a percentage correct of 65%, and a d prime of 2 corresponds to 85%. So the percentage of correct trials that the model observer performed. Now, a bit of historic development, so how the channel mechanism made its way into the practice. So initially, there was the model observer, which was called the ideal observer. However, this one was computationally almost infeasible for common images. But then Myers and Barrett translated a concept from studies on human vision into imaging. And those studies on human vision that had shown that the patterns that were shown here, so these luminance patterns, they could be used to derive the line spread function of human test objects. And those line spread functions could be fitted by the difference of two Gaussians. And those channels now allowed a pre-processing of the image by a set of those channels that are tuned to a given spatial frequency. And this is similar to what those researchers found in the human visual system. Those channels are shown here for the example of those difference of Gaussians, on the left in the frequency domain and on the right in the image domain. To illustrate this generalization, I have an example here where we took the image with noise and subtracted it from the image with the signal to enhance the signal for this kind of illustration. And by using, for example, 9 channels, so the Laguerre-Gauss channels in this case, we can generalize the image and reduce the dimensionality from, for example, 128 times 128 down to 9 pixels in this case, so from the 9 channels. And if we take the step back, so if we take the channelized image and we back project, we can see at the lower right how the image is approximated by the channels. So the main feature is still there. After the introduction of model observers, we can now come to the method of dose efficiency. We want to use this method that we developed with the PTB to apply it as a type testing for CT devices in Germany. And the measurement that is specified will then be carried out by the manufacturer on 5 CT systems of the same type. In this process, a phantom will be irradiated with precisely settings, and the image data that we acquire are then transferred to a software that we are developing. And our plan is to create a web application that can be used cross-platform. The image data is automatically processed, which includes the definition of the regions of interest and also the calculation of the figure of merit. A dose efficiency label is then proposed, which is somehow similar to the European Union energy label known from televisions or washing machines, and also similar to the emission standards in the European Union, as we also want to define a threshold for this kind of test. The automatic image processing is illustrated on this slide, so one part of it, where we start from a batch of phantom images, and by taking the mean, we can highlight the low contrast inserts and also the contour of the phantom. And in a first step, by using image processing libraries in Python, we can detect the phantom by using an edge filter and a circle detection. And from the phantom that we located now, we can define approximate regions of interest where the low contrast inserts are located. And in a next step, we can then use a template matching procedure to precisely locate the low contrast inserts. So this leads us to the 4 regions of interest that we are interested in. In order to get the regions of interest with noise, we can just, for example, take the locations that are located between neighboring inserts. And with this, we have now derived the 8 regions of interest that we need, so 4 with object and 4 without. And those can then be extracted from all the images that we acquired. I already spoke about the phantom that is used for this methodology. Here we can now see it in detail. So the CCT189 is a commercial phantom, which was specifically developed for low contrast studies, and it was recommended by a task group of the MITA, so the Medical Imaging and Technology Alliance. And here in the 3-dimensional sketch, we see the contents of the phantom, and we only use the small ones that are colored here. The measurements were performed by using the settings in the table at the bottom. So we used the protocol for the abdomen and used the settings that are specified and repeated the whole procedure for 3 dose levels, so 2, 6, and 12 milligray. And by using the images that we acquired for the 3 dose levels and by using the 4 low contrast inserts, we could get 12 values for the detectability by our model observer. And in a first step, we average over the dose. And in a second step, we take the weighted mean in order to get to the dose efficiency index that we propose. To sum up the methodology, I have here a slide which illustrates the process again. So starting from the images and the channel matrix, we can get the channelized vectors that are then combined with the template to get the decision variables or the observer response. From those, we come to the probability density function, and we can calculate the detectability. Now we need to repeat steps 1 to 7 for the other dose levels and can then take a a first step towards the dose efficiency. So we have the detectability shown here on the y-axis and the dose on the x-axis. And by approximating this integral by the trapezoidal rule, we get to this intermediate value. And by repeating those steps again for all the low contrast inserts, we can in the end take the weighted mean, and we use the diameter and the contrast of the low contrast inserts. With the methodology now completed, we can look at the results. So in 2018, an international comparison was performed involving 13 institutes, and they all had to implement a model observer. The researchers acquired scans of a water phantom using also an abdomen protocol, and they subsequently added structures digitally to the images. And those images were then sent to the participants, which implemented a model observer and sent the results back. Those results were then sorted by the detectability for each of the 3 low contrast inserts that are shown at the top, and they showed a fairly good agreement with some variation. We repeated this evaluation with the same image data to check if the results from our implementation agree with the results from the study. And here in blue are our results, and they are quite close to the median value. The next results that I want to show were produced by using the CCT189 phantom, and we gathered 3 specimens of this phantom type, which are identified by their serial number here at the top of each subplot. And we scanned those on our CT system to check the reproducibility of the method. So we have a subplot for each of the specimen, and on the x-axis we have the 4 repetitions that were made under the same conditions. And as it's clearly visible, the 4 repetitions for each specimen are nicely within the uncertainties, which proves the reproducibility. However, if we compare those 3 specimens, we see a clear difference. And therefore, we measured the contrast values of the specimen, and those measured contrasts deviated from the nominal values, even though all 3 phantoms are of the same type and from the same manufacturer. A correction based on the nominal and the measured contrasts enabled a comparability. And from the left, where the differences were up to 30%, we reduced them to below 8% on the right. We also found the same results for the phantom CCT191, which is another type with slightly different specifications, and those are not shown here. We also performed a measurement campaign where we aimed at covering a range of different scanners and different manufacturers, and we wanted to get a distribution of the dose efficiency for those range of CT devices. We have used different reconstruction algorithms, which are shown in the legend and are depicted by different markers. So the filtered back projection, the 2 iterative algorithms, and a deep learning iterative reconstruction. And we had 5 different manufacturers, which are depicted here by different letters on the x-axis. And the different CT systems were numbered on the x-axis. To show some of the findings, I now reduced the plot a bit. So now we have a comparison between filtered back projection and the hybrid iterative reconstruction. And for all the devices that offered both, we can see here that there's almost no difference in terms of the dose efficiency index. So there's almost a similar performance, and this also agrees with the literature. However, if we look at the model-based iterative reconstruction, we can see that is the overall tendency is that it's better in terms of dose efficiency than filtered back projection and the hybrid iterative reconstruction. However, not in all cases it's significant. To conclude, we detected significant differences between the specimen of the same phantom type, but those could be handled by a correction. Additionally, we showed the reproducibility of the method, and we performed a measurement campaign. So the presented methodology can be used to determine the dose efficiency of CT systems. The next steps include the creation of the web application, and we also plan to make the software open source. And in order to use it as a type testing at the manufacturer, we want to include it in a guideline. And for those interested in the method, I have here our publication and a QR code. And I, last but not least, want to thank all our partners that cooperated within this project. And with this, I'm ending the second part and hand over the floor to Matthias.
I will talk about a method which should complement the dose efficiency method suggested and presented by Maximilian. And this attempts to derive image quality parameters directly from patient images, and it makes use of non-parametric statistics. I will first explain why we would attempt such a thing, and then how, and illustrate how this works with examples from mammography. As you may have noticed, using model observers needs quite a lot of work, so many images are needed, and that's why it is intended for type testing at the manufacturer's site and not at the clinic. But one would also like to have something, how one could check the quality at the clinic. Another challenge for the model observers is that with a reconstruction methods which are based on artificial intelligence, it may happen that it may not work that well with the technical phantoms that are used for the approach just presented. So then on the long run, one would probably need anthropomorphic phantoms, which would be more difficult to get there, difficult to produce, and it's not readily available like the technical ones. And finally, the relation between the radiologist's assessment and the detection probability yielded by a model observer may be system dependent. But that's not quite sure. But nevertheless, one would like to have something in addition to the model observers and the low contrast detectability. And what would be nice is that we get these parameters directly from the patient image without having to take extra acquisitions for quality assurance. These measures should be objective, and they may be task-specific in the sense that what signifies a good image may be different depending on the diagnostic task. What parameters would be needed? First four one would think of is, of course, contrast and noise. Without a contrast, you don't see anything. If it's too noisy, the contrast will not be sufficient, and therefore it would also be helpful to measure structuredness in some way. As Hugo pointed out, the noise structure, for example, has an important influence on the detectability of lesions, and also the sharpness of the image would be of importance. Let us first look at the contrast. What we know is if we have, for example, a step function that is used, for example, in quality assurance in mammography to calculate contrast and contrast to noise ratio, then we have two well-defined regions with lower and higher gray value, which the histogram of which you see on the right side. And you can define a mean value and a standard deviation in both regions. And if you calculate the difference between the means and divide it by the sums, then you get the Michelson contrast, which can vary between 0 and 1. That's what we all know since university times. And what do you do with an image like that? This is a region of interest extracted from a mammogram of an anthropomorphic phantom. And obviously there are no well-defined regions where you have the higher and the lower gray value. So what can we do with that? First, we can look at the step in a different way. We have this step function, we have the histogram, and by using, for example, 𝐂𝐡𝐚𝐩𝐭𝐞𝐫𝐬 method, we can set a threshold between high and low gray values, and then look at the so-called order statistic, which sounds fancy, but is nothing but taking all the gray values, ordering them in ascending order and plotting them. And if you make this plot of all gray values in ascending order, and you draw a line, a horizontal, which is given by the threshold you have just defined, then you see that there are two areas, A1 and A3, which are enclosed between the order statistic and the horizontal given by the threshold. If you divide the sum of those by the areas of the appropriate quadrants in the graph, then you can define a quantity we called a relative gray value distance, or delta. Again, if you use this and multiply it by the range, so the difference between the maximum and the minimum gray value, and divide it by the mean values, 𝜇h is the mean value above the threshold and 𝜇l is the mean value of the gray values below the threshold, you can define a quantity CED, which stands for contrast equivalent distance. Let's look at these two simple examples, a sharp step, and the lower image is a simple ramp. The histograms obviously are different. In the top level, you have these two distinct peaks. Below, you have a continuous histogram. And the corresponding order statistic also looks different. It's a kind of step function in the first case and a simple line in the second one. And from the definition of delta, it's clear that in the first example, in the step, you have a higher value of delta and also a higher value of CED than for the ramp. Accidentally, the CED in the first example is equivalent to the Michelson contrast, which would be 2 minus 1 divided by 2 plus 1, which is just 1/3. If we compare now CED and Michelson contrast, for the step, it's almost the same thing. But for the image, the ROI of an anatomical image, you see that you can define and calculate a contrast equivalent distance, but they have no way to calculate the Michelson contrast. For low noise, say that when the signal distance to noise ratio is higher than 3, this contrast equivalent distance converges to the Michelson contrast. But when noise is very high, then a CED rather measures the standard deviation of the noise. So that is a problem, but this is a price you have to pay since you want to apply this on patient images and not only on steps. As an application example, I show here a comparison between two mammograms. Left, it's both are the same mammogram of anthropomorphic phantom at an exposure chosen by the automatic exposure control of about 71 milliampere seconds. Left is the for-processing image. On the right, it's the for-presentation image. And as everyone can see, that the processing has done good because the contrast is much higher now. But we can measure this now with the new quantity CED. If we evaluate this on small regions of interest of a size of 32 times 32 pixels. And we calculate also the ratio of the 4 presentation to the 4 processing image. You get the color bar on the left, you see. And you see that there are regions where the contrast enhancement is almost not present. It's 1, namely at the skin-air boundary, where the contrast has already been very high. So there's no enhancement, but the processing has done good. Where there's the glandular tissue, you have contrast enhancements of up to a factor of 12 or 13. And you can summarize this by using, for example, a box plot. The median of the contrast enhancement is about 8. 50% of the regions have a contrast enhanced between 9 and 4. And there are some extremes going down to no enhancement at all and up to a factor of 13. So you can quantify now contrast enhancement with this new quantity, which was not possible before in this way. So for contrast, we have an idea, but we saw that to evaluate contrast, we also need to know something about the noise, which we will have a look at now. We have proposed a noise parameter tau, and this is obtained just by counting. If the image you see here is just white noise, and if you look at 1 pixel, in the middle, pixel 0 and its 8 next neighbors, you can have a look whether this central pixel has a value which is different from all its neighbors by a certain amount t, a threshold. And if this is true, then you count it for a certain threshold, and then you increase the threshold and continue. And if you do it for all pixels and many thresholds, you can get a curve like this on the right side, which shows the number of pixels which fulfill the criterion as a function of the threshold value itself. You see that for a lower threshold, you have more pixels, of course, and for higher, you have fewer, where this condition is fulfilled. Now, if you take this curve and you calculate weighted mean of the threshold and use the number of pixels as a mean, as a weight, sorry, you get this quantity tau. And it turns out that this quantity is proportional to the standard deviation of the noise. And just as a reminder, it's an unbiased estimator for the variance is given by this formula, which you all know. But you may ask, why bother? If I can use this simple standard deviation formula, why use this complicated tau stuff? Let's look at white noise again. For white noise, the ratio between tau and sigma is about 1/2 or 2 if you look at the other direction. Sigma is about 2 times larger than tau. Interesting is if you have not just noise, but some more or less interesting structure underneath your noise. If you naively calculate the standard deviation as before, you get a value which is 30% wrong. In case of the tau, on the other hand, you have just a difference of 1.4%. This is something where you could well live with. So tau is almost unaffected by background structures. I'd say almost, but let's see how this works with mammograms. In the publication I indicated below, we have demonstrated by comparing anatomic phantoms and equivalent homogeneous phantoms that the noise parameter we get from the homogeneous and the anatomic ones is identical. In these 3 images, the middle one is again the AEC exposure value of 71 milliampere seconds. On the left, it's 30 milliampere seconds less. On the right, it's 30 milliampere seconds more. And if you calculate tau, again on a scale of in ROIs of 32 times 32 pixels, you get these heat maps. And you have to look at the scale, that on the left, the noise is much higher than on the right. And you can again summarize this by using, for example, the box charts. So also noise can be measured locally in mammograms using this new quantity tau. The limitation is that caused by the definition, it measures just the white part of the noise. So somehow one would also need to measure the structuredness or the structuredness of the noise, if that would be possible. And let's have a look at that now. One way to deal with this is to look at the so-called relative mutual information of co-occurrence matrices. Due to time, I will not have the time to go into details here. I will rather try to give a hand-waving a feeling of what this quantity does. The three images you see here is white noise on the left, or almost white noise, and more correlated noise on the other ones, corresponding to, say, CT images with iterative reconstruction or more. And one way to try to handle this is to segment these images first using a threshold. Ideally, you would use the same threshold that you've been using to calculate your contrast. And then you have just black and white pixels. And then you can calculate probabilities. If you look at the pixels, how probable is it that a black pixel would have a black neighbor, a white pixel would have a white neighbor, and if a pixel would have a neighbor of different color. And for a segmentation into two levels, you would get a 2 times 2 matrix of probabilities for your neighborhood. And from that, you can calculate by going via entropies of this distribution, you can get this quantity U, the relative mutual information, and you see that for white noise, it's almost 0, whereas for correlated noise, this quantity goes up. And this idea I took from a paper by Novosad and Stepinski from a journal called Landscape Ecology. Nothing where you would look first if you're dealing with medical images, but they used it to classify landscape patterns, and it also works to classify noise or structuredness in images. And you can, of course, apply this quantity also to the three images I've shown before, the mammograms, and you also get now these heat maps for the mutual information. U can vary between 0 and 1. And you see that with increasing exposure, this means increasing dose, the median mutual information increases, but you also already see that this is going to saturate, so it will not go up to 1 with these anatomical structures beneath because of the structures of the tissue. So we have three quantities now for contrast, noise, structuredness. What we still need is sharpness. And we also need to understand better how these parameters are interrelated. I already indicated that the noise interferes with the contrast. The noise also has an influence on the relative mutual information. Information and contrast are independent, and we do not yet know how the sharpness will interact with the other three. So what we still have to do is to define a quantity for sharpness. There are some first ideas using wavelets. You see here for this smooth transition or the sharp step that you get something which has a higher value at the sharp step, but this is only in the first development stages, but we have some ideas how to handle that. And the interrelations, as I mentioned, will have to be understood. Multiscaling is also something which we would have to look at, because the quantity, how ordered something is, may depend on the length scale you're looking at. And of course, it's also important how these parameters will be related to an assessment by the radiologist. So this is all still to do. And if there are questions, I'm ready now with my presentation. We have here, in the presentation, there will be the links to the 3 papers, and I've also added links to the software. So if any one of you would be interested in playing with these parameters themselves, there's a link to the MATLAB Central where we published the necessary software. So you can go ahead and also use these QR codes if you wish, which are also in the presentation. And I also want to thank all the people who have contributed. It's my colleagues Marcel and Franziska from PTB. It's also colleagues from the Technical High School in Gießen, from the Reference Center for Mammography in Gießen, and Johannes Sichopoulos and Ruben van Engen from Nijmegen in the Netherlands, and also my colleague Clemens Elster from Berlin. Thank you.